Thank you. So thank you for inviting me to give a talk. What I would like to talk about today is, on one hand, how to deal with dynamic environments, because what you see a lot these days is that people are trying to recover structure of the environments, but they are not bothering a lot about the dynamic state of what's happening in the world. And I would also like to talk maybe of different ways of extracting the visual information, which allows us to interact directly with the control of the vehicle. A little bit of my background, if computer switches. No, let's do it here. My group is basically doing research in all types of perception, starting from visual navigation, service robotics, mobile robotics, cars, but also medical robotics. We try to get low-level perception to work. That means we interact a lot with biologists to understand basically how the perceptive field of the eye is used directly to control systems. We do a lot of scene analysis, in this case for manipulation, but of course in car scenarios also to understand, to label things in the scene, and registration to understand basically how which objects are in the scene and how they are maybe how they got modified over time. My more recent work is more towards understanding what's happening as actions in the scene. So I use robots to observe what's happening, and what we also do is we work on perception systems in themselves. So building cameras with extended field of view. So these are omnidirectional cameras of a special kind, which can replace insect eyes. We do sensor substitution, how to actually measure also physical properties of the environment using passive sensors. I will get a bit later to it. Like if you use the camera, what you usually get is just the geometry. What you don't understand is basically what's the mass distribution, what's the density. My example was actually a trip to US coming from Bavaria. I was used to the 1 liter Steins in Munich, and we went to a brewery and we got a plastic mug. It was a pitcher. I thought it was just for myself. It was for 5 people. I tried to lift it, and of course, I miscalculated the mass. It was a lot lighter than I expected, just because I could not estimate the mass correctly. I think it's important also to understand the physics of the scene, and we do some work also in this field. And I used to have a second life at the German Aerospace Center, which is close to Munich here. They do a lot of course, space robotics, service robotics, medical robotics. And now I switched to the Munich School of Robotics and Machine Intelligence. And you will see a few examples like the mobile car here. This is something I will use for my talk here. Flying systems, just to motivate a little bit of a dynamic perception, and also 3D reconstruction, scene analysis. I couldn't believe I was doing the project here. I thought it was a joke when Professor Hitzeke suggested it to me. It is actually an 11-ton Dragon with a diesel engine, which was supposed to be navigated through space. And it was actually pretty challenging to actually put such a big robot on the car. So there is a festival here close to Munich where a knight fights the dragon, and the dragon should not kill the horse. So what I would like to talk about today is actually what are robust ways actually of connecting sensors to actuators and how to deal with the scene. So on one side, we have our IMUs, we have our camera systems, and we have our LiDARs, you name it. And on the other hand, we want to control something with these sensors. And in my opinion, we have 2 ways actually how to connect these 2 sides to each other. And what most people do, just because it's easier for humans to understand what's going on, is to abstract the sensor information to 3D and use the 3D information for planning, for mapping, for logging information. And from these maps, actions to the actuators are derived. What's the problem with such a chain? The 3D is not a native space of a camera. That means abstracting the information creates already errors due to calibration errors. The same is true on the other side. To go from the metric information to the actuator, you add additional errors to it, and you deal with quite a large error between what you see and what you interact with. So I'm looking for a different way how to actually combine directly the sensor perception to actuators in a more native way. We will talk about this in a moment. So let's start with the car. We actually built the car ourselves. Well, it's DLR, the German Aerospace Center. The car is actually a 4-wheel robot, 4 independent wheels, which can turn in any direction. Of course, they need to agree on something useful to be a car. The funny part is the car can really turn around any point in space. Sometimes it needs to stop to change between the orientations, but it's very flexible in what it's doing. And you can drive it by wire, sitting inside of the car, or you can do autonomous driving, what we were doing. Due to the strange design, we needed 18 cameras on the car just to have a complete field of view. And the car is moving, can drive like a regular car, or it can do, for example, this. So this is something you don't see on a regular car. It's really just avoiding an obstacle by shifting to the side. Trust me, you don't want to sit in the car when it's doing it. Your stomach is not really used to this type of motions. What's a very practical thing for Munich actually is this feature of the car. This is driving autonomously. So we are using here basically the reconstructed geometry of the space just to park the car in a parking lot. So we will see that for different types of interaction, we need different types of perception. If to navigate in a parking lot, it's of course optimal to do 3D reconstruction because there is no motion, or almost no motion. You can see the car slides in and it's parked. You don't want to be the other car because it may be difficult to leave. So this is the car we used for our processing. And now basically to understand what's happening, the first thing was of course to do visual navigation. I mentioned already at the beginning, I'm a dinosaur. So I still believe in traditional vision just because we can extract not only the information, but we get a lot of information about accuracies and covariances which are required for fusion. So this is a system we built 2003 for navigation. Actually, Professor Hitzinger asked me to fly with a drone around Schloss Neuschwanstein, and I was too lazy, so I mounted a camera on a robot and took just up to scale model of Neuschwanstein, proving that the system is working. So it was a little bit of cheating here. Well, the problem with the system I've shown you there is the system was giving me just position information without telling me how accurate it was extracting the information. And it was treating all the features in the image with the same weight. If you think about what you perceive while walking, you know that objects which are close to you have a larger motion in your optical field than distant objects. It goes all the way to no motion at all, where all you get from the object is just information, rotation. And this is actually what biological systems are doing. Here you see the small owl is exactly doing this. It's trying to decouple rotations from translation. So it's trying to keep the head stable. And we try to actually see if this can help us to build now a robust navigation system. And of course, it did. Let me just see. So what we see here is basically something which has features on it. And we see the optical flow, which we observe in the camera, is basically a combination of 2 motions. So let me just play it again. So this is the tree. The first motion in the optical flow is basically due to translation. The second motion is due to rotation. And what you see in the camera image is basically the combined flow, which doesn't make much sense to the human. But once we are able to compensate the rotation in the flow, suddenly all what remains is the translational flow. And this gives exactly the property I was just mentioning. Close objects, large displacement, distant objects, almost no displacement at all. That means to find the intersection point, we really can here put a larger weight on errors to long lines, and we could allow larger deviation from the intersection point for short lines. So we can put more weights on a more accurate information. And this type of processing allows us also to build a covariance matrix. And this is exactly what we are building. to navigate drones. So sorry to keep drones, but I think it's more, in this case, it's more challenging than car. It has more degrees of freedom. So we used a drone like this here to navigate basically 8 megapixel back then camera. So we mounted the camera and we're flying with the camera in the outdoor environment. We had here 8 propellers, and with the way it was built, nothing was in the field of view, so we could actually have a complete view to the. So what we did was we acquired with the camera 60 images, by telling the camera to take an image every 20 seconds. And now use this optical flow system. So the green lines, I hope you can see them a little bit. The green lines are optical flow lines. And from the calculation I just explained, the system could recover the blue flow, which is basically just the translational motion the drone was doing between 2 images. And the intersection point was here. So this is basically the direction of motion in which the camera was flying. And we used it now to build from the 60 images this 3D model with an accuracy of 1.5 centimeters. So you can see here in this model, even the solar clock on the tower, somewhere here. I noticed the solar clock only after looking at the 3D reconstruction. There was a small notch sticking out of the wall. So this is basically something which you can do basically with a monocular camera just by stitching information from images. To show the accuracy, we used it, of course, also to stitch information between different image frames. So one application we used in museum a lot was to reconstruct 3D information just by looking at how a laser line is deflected. So a light section laser system. And while sweeping the line across the object, we could get a 3D model. Of course, you see that for each motion, each line had to be registered very accurately to each other. And here you see the system in action. This is just to show how accurate the system can be. And this is the worst case you can imagine, because you have a system in the human hand operated very close to the object. So the system needs to really perform really well. I hope you can see the 3D image of the statue showing up here on the top of the image. So we are able to get 3D models. And now to show you basically how much processing power is wasted actually in deep learning is, I applied this algorithm with a relatively recent graphics card. So running just the image detection on the graphics card allows me to run 120 Hertz frame rate navigation system with 3D reconstruction. And I'm using just 10% of the graphics card. So I can use also some other processing here. And you see the system is plotting basically, this is the Kitty data set you've seen in some of the talks before. So we seem to be able to get motion information, but only in static environments. Once we have this motion information, we get also 3D. So camera can provide us 3D point clouds. And now comes the second point here in the processing is basically what can we do with the 3D point clouds? What we see a lot these days is actually this part of the processing, labeling. You can do some basic segmentation, and then you use model information to put labels on the object. So this is something, of course, which is very useful to know who I interact with. Is it a biker? Is it a car? Is it a bus? Or is it a tree? But what's of a lot of interest for us as well is to understand how the objects are moving in space. And these two fields is something I want to cover next. So what we built a couple of years ago was actually shown in the Hannover Messe. This is a robotic fair in Hannover. We got the best prize for robotics for this. So basically, this is a system which can find objects in a cluttered scene. Again, no deep learning. It's using directly 3D information and a ransack system to fit different models. So it has a set of 3D models in a database, and it fits these models in strongly occluded environments and gives you directly as an output 3D pose of the object. So we use basically the shape to find the object in the scene. And once we found the object in the scene, we have additional information now, which tells us how to grasp the object, what type of actions you can apply to it. This is not going towards what we are interested here, but I wanted just to show you the performance of the system. Well, I'm sorry for putting this in a manipulation scenario, but I think this is more challenging than having just cars standing here around. Let me just find some. There's somewhere. Here. I call it Chaplin movie. It's kind of recording a little bit faster, so I don't want to waste too much of your time. So the system is really cleaning, finding objects, getting 3D information. So that means you can deal now with 3D objects. The problem is, of course, you don't want to have 100 instances of the same object. You don't want to have all the possible cars which are on the street in your database to be recognized. The same is true for manipulation. In my lab, students break the cups, so I don't want to have 100 different cup models to know what's going on in the kitchen. I would like to understand basically how to generalize from some model I understand to what I see. And this is the formable registration we built, which is basically taking an object and deforming it to fit the object I see in the scene. And this gives me a deformation heat map, which tells me how close is what I see to what I've previously seen before. And this allows me to actually move information from the database where I may know maybe how to grasp it, where the doors are, what are the typical dynamic behaviors of the object. And now I can see how similar is the new one, which I see in front of me. And I can decide how many of the parameters I still want to accept as something which is valid for the current scene. Now, up to here, what I was discussing is basically things which were dealing with static scenes. So I was trying to find my position relative to what's around me. And I was trying now to reconstruct 3D information of things which are around me, so to put names on it. This is something where the vision algorithm does not have too much of a time constraint. If it takes a little bit longer, the system will not hurt the system just because your step size is quite large. What we used the systems for back when we were doing the experiments is to stabilize actually a drone. So our vision system was supposed to be now directly providing signals to the controller. And here the world changes significantly. Once you want the vision to actually interact with the controller, you will notice the vision is too slow. So we had to work on things, how to actually build a vision system which will interact directly with the controller to stabilize, for example, the flips of the drone. And the only way to do it is actually to switch to a system which is not based on the camera, but it's based on inertial units. So it's taking an inertial unit, it's integrating the accelerations the system is measuring and outputting them as a position. It's using the camera only to compensate drifts in the IMU. What's the advantage? The advantage is the output here is 30 Hertz. The output here is 1000 Hertz. So I'm a lot closer to my control algorithm, which I want to use. So basically, this is something, as I said, we are used to stabilize drones. What we did here is, for example, an experiment where the system was flying on a triangular course, and we switched the camera off for 5 seconds while the system was going translational motions, and we switched the system for 1 second when the system was doing a rotational motion. And the way we were fusing the data in our system allowed us to actually still keep the error under 1.2 meters. Sounds a lot, but without the fusion, it would be 25 meters. So the system would be just somewhere. And the system is really now able to compensate dropouts of the camera. Why is it important? In the car, typical situation, you drive into the tunnel, you drive out of the tunnel. What happens is that the camera needs to adjust to the change brightness, so it's blind for several seconds. In this time, you still want to have some control system, and this is what the system is providing. So the drift will, of course, increase over time, but the system is still able to operate in this changing light conditions. Here is an example which was very funny. Like we started in a container here. So this is basically, I hope you can see my mouse, in a container building, and the drone had to fly out of the window. So had to fly, find the window, and then was flying basically outside through the inner yard, found the door, and flew back to the original space. The only way how you could do it, stabilizing the drone basically with a visual system, was A, to rely on IMU and compensate just the drift, and B, have a system which is providing correct fusion so that the system will not diverge in this 3 to 4 seconds while the camera is switching from dark to bright and bright to dark. No? Oops, here's my 2 slides. So this allows us, of course, now to build systems which, well, this is something we see a lot now. Let's just replace the drone with a car. You take 2 snapshots from 2 positions of the camera, and this gives you the 3D structure of the environment in which you're flying. Well, this is something which many people are telling you a structure from motion approach. What many people forget is this thing will not work if the object you're observing is moving. Just because the 2 images, you take the 2 images at 2 different points in time, and sorry, now my computer is. You take the images at two different points in time, and in the meantime, the object moved by some unobserved velocity, and what the reconstruction will be completely wrong. So structure from motion approaches, reconstructing moving cars on the road just cannot work. Just because there is an unknown, of course, you can assume that the car is moving straight forward, but if the car is doing some zigzagging, this will confuse your system. We built actually something which allowed to reconstruct the motion of the unknown objects, taking not 2, but 3 camera images. We can go into details if someone's interested. But structure from motion in dynamic sense has a problem. What we were also doing is we were trying to synchronize the drones, the clocks on the drone. So let's take 2 cars maybe and observe something which is moving. But the problem is the clocks are not running with the same time. So the time offset between here and here will not release the camera at the same time. You get the same problem as with structure from motion. Dynamic scene will not work. And this is something which is basically the challenge where I'm working on now, is basically how to deal with dynamics in the scene, what to do with all the cars moving around. So since I was working on, of course, this is work also of my students, I will mention them in the end. So what we did here is actually we tried to run fast feature recognition on low power processors. So this was an ARM5 CPU on the Beagle board. This was one of this kind of cell phone CPUs 10 years ago. And we built back then a key point detector, a feature detector, which is capable of running 100 hertz on this CPU. So this CPU is 10 times slower than your desktop computer, and it was still capable of running 100 hertz. This is an August feature detector, which is now part of OpenCV and used in many detectors. So this is something we developed to have something fast. And now to deal with the scene, we want to have very fast observation. So I've shown you already that we can navigate basically our system with very high frequency, 120 hertz. But from a monocular camera, it's impossible to get depth information. You get basically a 3D model, which is up to scale. There is an unknown scale which needs to be resolved somehow. And in my system, the scale is resolved by a second camera, which occasionally takes a snapshot in the scene and injects the scale to the system. And this allows us now to basically make fast observations of the surrounding world. just a small side effect. So I just want to motivate basically to look a little bit more in what is actually in the image directly. Doing all this pre-processing in vision removes a lot of important information, which, as you will see, sometimes helps a lot in navigating your systems. So here, for example, my navigation. So what can you do with one camera image? As I told you before, from one camera image, I cannot really extract any motion just because I have a single snapshot. It's not really true. If you have motion blur in the camera, suddenly you have additional information which can be used directly to understand how things are moving in the scene. Well, many of you have math background. I guess it will look familiar. If an object is moving in the space during the exposure time of the camera, then the picture of the object will just smear over the image. And what happens in the image is basically a convolution of the image with the path how the camera moved. Well, convolutions are usually something where Fourier is actually a good way to analyze. So if you turn it into Fourier space, you will see that the blur in the image is a combination, is a product of the image Fourier transform and the Fourier transform of the motion. And now if you actually extract the Fourier transform of a small patch here in the image, if you do just block, you will do something like this. Just because you cut off a block with sharp boundaries, this gives you this artifact here. If you put a Gauss filter on it, suddenly you get some substring function like this. And this tells you directly in which direction the current patch is moving. The patch is moving in the direction of the small diagonal of the ellipse. And it tells you also what's the magnitude of the motion. This is basically the width. So suddenly from one image, you get for free motion information, which was lost if you would just do your feature extractor. But you can do more. You can, what I'm showing before is basically something which is doing a metric reconstruction and navigation. This is basically moving a robot in the scene. It's actually my PhD, it's very long ago. In a metric environment. Problem here, of course, once you lost the calibration of the camera, everything went terribly wrong. So a lot easier is to couple basically the image information directly to the control signal. So an error in the image should correspond to some response of the robot. This is known in manipulation as visual servoing. You try to actually servo an error in the image to 0 just by using a Jacobian to map error in one space to error in the other space. And this is something which allows you already, which is the first idea how to actually couple now camera to the actuator without going through 3D space. Using these Jacobians, you don't need to transform to the metric space. You can couple basically the space of the actuator directly with the space of the camera without accumulating errors over the chain. So how does it help me to deal with the cars? So now basically you have all these scenes where cars are navigating around. And my problem is that I would like to look far ahead. What's happening 50, 100 meters ahead? That means my cars are not 200 pixels, they are maybe 10 pixels big. And at these distances, if you look at the stereo system, most robotics people are used to operate basically in this space up to 8 meters. So this is basically what the camera can read, the displacement between left and the camera in the image, depending on the distance of the camera. You see that there is a useful information very close. The farther away you go, the worse it gets. And at 100 meters, you're just basically reconstructing noise. So what you can do is you actually can increase the baseline of the cameras of the stereo system, which just pushes the signal more towards higher values. But there is only so much you can do. So here helps if you actually not just sitting in the lab and do your engineering job, but go sailing from time to time. Well, every sailor knows that there is something called steady bearing. What does it mean? if you sail and you see someone always at the same position, then you collide with him. It's a rule every sailor knows. Engineers forgotten about it. So what does it mean for me? To detect collisions, all I need to do is just basically see if something is always at the same position on the camera. If yes, I'm colliding. I don't need to know where the object is. I don't need to know where I am. I don't need to know the velocities. This all cancels out. And actually, I push the system a little bit further, and I can tell basically that if some point is moving with the velocity v, then the object belongs to a plane where the velocity vector is the normal. And I can estimate how many frames it takes until this plane sweeps through the focal point of the camera. And I can also tell what's the miss angle to objects. So will I actually hit it, or will I just pass by it? This helps me to prioritize objects in the camera image. I have absolutely no information about focal length, nothing, no training. I'm just really clustering the optical flow. And this actually clusters of moving cars for free for me. So I get basically clustered object on the scene of independently moving cars without, what I know is basically that this is the car I will have to deal first. This is a car which I will have to deal second. And for this car, I got actually an information that I dealt with this car before because the car is moving faster than I am. The whole information is stored really just in the image. And we can use it now to do dynamic obstacle avoidance. So here, the system is using one monocular camera, not calibrated, and it's avoiding obstacles, static or dynamic. So to prioritize things in an environment, I can use this system without any calibration, which means if the system actually gets some shock during collision, the system will still recover because even if the focal length changes, the system will adapt to it. I don't need to recalibrate. The system is really just using the geometry of the projection. The problem you're having here is the system doesn't have metric information. That means you need to redesign your control. And this is something, this would go too far because it's supposed to be a perception talk. We designed a controller which can actually operate now with this new type of perception. And the system was now used, hope it's running, to avoid obstacles. So basically, it's really just detecting optical flows and it's avoiding static dynamic obstacles. Of course, it can do it just because the car itself is moving. So if the car is moving, this type of processing is really good. If the car is static, like in the parking lot, we switch to stereo processing because then the geometry reconstructed from the camera is more accurate. And for parking, of course, I am also in a domain up to 5 meters where my system is giving me the correct information. So here is some other implementation of this. Yeah, well, we are not really the control guys, so I'm pretty sure you can do better than what we did. This is like computer scientists controlling a robot. The car is also very expensive. It was 1 million, so we tried not to destroy it. So that's why we took boxes and not other cars. But I validated the system now on many other things. And what's nice about this, I can now build a completely different map, which has one coordinate of the map is time to intersection or to this interaction when the plane will intersect with my camera. And the second coordinate is just angular angle from which the object is coming. The advantage of this map is that the objects, if they don't change dynamic state, they stay static in this grid. The whole grid just scrolls towards me because with each step, the time to interaction gets reduced by 1. So I can use my static planners to plan a collision-free path in a dynamic state. I don't need to do anything special. We use it to understand, for example, what's happening on the road. So we get some information about interesting points on the road just from parsing an open map. We get information where are stores, where are intersections, where are pedestrian crosswalks. And the second information we are getting for cars is basically analyzing now time to interaction, for example, with a pedestrian. So I see, although the pedestrian is here, the system is blending that this would be our interaction region. So I will meet the pedestrian in this place. And now comes our game theory. Once you know that you interact with something, the whole driving becomes kind of a game competition. You compete for resources. So if you actually try to cross, if the pedestrian tries to cross a pedestrian walk, this is a resource. He or she competes against the driver. So if they discover that the time to interaction is 0, so that they will meet, they may respond to it. So the pedestrian may slow down, signaling the driver that he will not really try to run ahead of him, or the pedestrian can speed up. So basically analyzing just the time to interaction tells you directly the intention, what's happening in the world. Without ever knowing where the intersection point is, you know it, but you don't need it for your calculation. You just estimate basically directly evolution of pixel signals in the camera. So what I tried to convince you is basically that there are two sides of the medal. On one hand, of course, it's very important to get metric information to navigate in a metric space. This is important for all the logistics like parking or navigating through traffic jams, because the motion of the car is very slow and the signal you would get in the optical flow is very tiny. But once you get higher speeds, you would like to look more further ahead than just 5 meters. And in this case, the stereo geometry will not work anymore, but you can switch now to this different perception, which is giving up on the metric reconstruction and is going towards this perception responses. So the time to collision is nothing new. This has been known since the 80s or 70s. And it's really based directly on the pixel information in the image. You don't need any calibration data to calculate. And well, the other thing is what we try to understand is also driving as being kind of a resource competition where we try to apply a game algorithm on what's happening on the road. So this brings my talk to the end. It looks like I almost managed on time. I'm now ready for questions.